Hello everyone. So the purpose of this video is to discuss and kind of sample what we will be doing in lab 4, which is about isotopes and atomic mass. So this lab is completely auto-graded and you should have unlimited submissions for every single question. I just made sure of that. This lab does use a simulation from PhET, which is a website that has a lot of really cool interactive chemistry simulations, and you'll see which one we're using, but just be aware that you will be kind of using a different technology compared to just looking at the videos, right, in the previous labs. So you notice that I have two of the same exact page open here on a split screen, and that's for a reason, because I want to have the simulation on one side and have the questions on the other so I can scroll through and it's not me scrolling up and down too much. So the purpose of this lab, we are defining what isotopes are. We are going to learn a little bit more about atomic mass and mass number and get to explore, how each are affected by each other. And we will calculate atomic mass using relative abundance of isotopes. So the first part is about isotopes, so part 1, and then part 2 atomic mass, and then part 3 finally you are calculating atomic mass. So it kind of leads there, one part at a time. Always take it one part at a time. So you are first going to open the simulation. It will actually look like this on the right hand side, where you have to click launch. So you would click launch and this is what pops up. So I'm going to have the instructions on my right hand side and I have the simulation open on the left hand side, just so that I don't have to scroll up and down. Like I said, I would recommend this if you want to do this as well. So you will first, it should show you this. So you can click view split question view. Wow, I should have figured that out earlier, but you can click this and it should show you the simulation next to the questions. Cool. Nice to know. Okay, so first we are working with isotopes, right? That's what part 1 is about. So open the simulation by clicking isotopes. Be sure mass number is selected right there. So we're just making sure we have the right one. And click the plus sign next to the symbol right there so that you can see both the symbol and the abundance, because it tells you how much of this particular isotope exists in nature. That's what abundance means. So we are going to have the questions. So here we first introduce what the symbol is. So hopefully if you've been studying for your chapter 4, right? You've been studying chapter 4. This is directly related to that. So in chapter 4, you learned about atoms and elements. That's exactly what this is about. So hopefully it kind of all falls together. But start off with the chemical symbol. This top number, and it's usually the bigger number, so keep that in mind, is the mass number, which it tells you the number of protons and neutrons added together. And then the atomic number is the number of protons. This never changes for a particular element. So for carbon, for example, the atomic number will always be 6. And then the mass number is the mass for that particular isotope. And then there's some more information. So let's try one of these questions, right? Number 1 was just, getting to know how to really work the simulation. So it told you to go to carbon, right? That's what we were talking about. Should have clicked that earlier. But yeah, you're just exploring. Number 2, add a neutron to the carbon-12 nucleus. So we will be grabbing a neutron right here, right? Right here is just the count over here is where we can grab an extra one and add it. Now, hopefully you notice this changed, right? This abundance changed. This also changed the mass number. Observe how the mass number changes. So we just added a neutron, right? And like I mentioned, mass number is affected by neutrons and protons. So right here it's asking which particles are counted in the mass number. I will let you work with that. Next, carbon-12 and carbon-13 are called isotopes. In what ways do the isotopes of carbon differ? So remember I mentioned isotopes, they are, or I mentioned how elements are determined by their number of protons, right? Carbon, it was a carbon before we added this neutron, right? It was carbon-12, right? Just a different version. Then we added a neutron and now it's carbon-13, but it's still carbon. So what is changing here, right? It's not the protons, because the protons are the ones that stay the same. That's how you give the name, right? That's how we determine it was carbon. So instead, think of what we just changed. So kind of simple. These are a little bit simple, but it's leading up to questions that you can apply that information to. So let's consider some of these isotopes. So how many protons does lithium-6 have? So how would you solve this? So you would click lithium and then you could count them directly right here. Another thing you could do is you could look on the periodic table and look at the symbol, and the atomic number, like I said, is usually the smaller value, and it's usually a whole number. It's not going to have decimals. That is your number of protons. So lithium has a 3, so I would put 3 right there, right? There you go. So go ahead and keep just using the simulation, using the information that you get from every single element, and you will be able to answer these questions. And definitely use your notes on what isotopes are, what mass number is, all of that. Okay, atomic mass, part 2. So hopefully you probably have gotten the gist of how this this lab is a little bit simpler than previous ones, but here we are back in the simulation again. So rebuild the carbon-12 atom. So we could have used the same one, but anyway, click atomic mass on the balance and then open this up because that gives you information. And then we're going to open up our carbon. We have our carbon-12. This reading reports the mass of the particle in AMU. Notice that carbon-12 weighs exactly 12 AMU. And it's because carbon was the element that we used to make that definition. So carbon is like, it's what we modeled everything else after in terms of mass. So they took a carbon-12, they not necessarily weighed it, but they calculated the mass of that, and it was, they decided 12, right? And then they divided that by 12, and whatever that mass was, AMU, is now the unit, which I know is kind of weird to think about, but basically the atomic mass unit, AMU, is defined as 1/12 of the size of a carbon-12. And what this ends up being is that 1 proton is equal to 1 AMU. And notice that carbon has 6 protons, right? So if you know that the total mass is 12, then that means 6 other AMUs have to be coming from the neutrons. So, and they tell you, add a neutron to the atom. Watch how the mass changes. So the mass went up by approximately 1 AMU. right? It went up to 13. So that's how you would understand that. Now, switching gears in part 2, you actually open up your mixtures right here. Select carbon and select nature's mix, right? The screen provides a visual of the relative abundance, right? So you can see there's a lot of purples, which are your carbon 12s, and then there's a little bit of green sprinkled in for your carbon 13s. So this is giving you a visual representation of how abundant carbon 12 is compared to carbon 13. So carbon 13, it just doesn't like to exist as much as carbon 12. So you can see that if we wanted to get an average of this, right? We can't just say, okay, you know, if I have 2 measurements and each one is 2 and then I add them, right? In terms of getting an average, right? The simple math way is just adding the measurements, dividing by however many there are, that's your average, right? Now here, we can't do that. We can't just take 12 plus 13, divide it up, oh, you get 12.5. No, because there's so much more carbon 12 in comparison to carbon 13, right? So instead what you do is something called a weighted average. By weighted, we mean you're taking into account how much of each one exists in nature. And you can see that there's way more carbon 12 than carbon 13. So here it actually tells you the average atomic mass. And you can see it's 12.01070. Notice that that is way closer to being on the closer to 12, you know, carbon 12 compared to carbon 13. And that makes complete sense because carbon 12 is 98.93% of what exists in nature. So of course it's going to be closer to that side. So that's what you would enter here. You would look in this little section. So what plays a role in determining the average atomic mass? Both the mass of the isotope, right? And then how much there is, right? So because there's more purple, it's closer to the mass of the purple, which is 12. And then I will let you explore the rest of those. Now, part 3. You will be able to mix yourself. So we saw previously that the average atomic mass, and so on. In the sim, click boron. But now we're going to be working with our own mixes. So my mix. And you will go ahead and build those mixes depending on what instructions it tells you and answer questions accordingly. So just make sure to use the correct amount of isotopes and the correct isotope, right? It tells you 4 versus 1, right? So just make sure to add the correct ones and then you'll have some math questions followed up by that. And then a really good example of how this is actually calculated. And you can try that atomic mass equation out. I do have videos on D2L about atomic mass calculating that, but if you would like to look up more, all you really need to search in, you know, YouTube, for example, is calculating average atomic mass or weighted atomic mass, and you'll find a lot. So that's about it for this lab. I was about to end the video, but I kind of want to talk through this equation here. So let's talk through it and then we'll end. So the relative ratio of each isotope is basically whatever percentage you have. So remember in nature, if you go to nature's mix, it tells you the percentage here. And I know that's kind of hard to see, but if you are on your own screen, you know, and looking at the sim and it's not so small, it tells you the percentage right here in this percent comp box. The way that you calculate the average atomic mass or the weighted atomic mass, that's the same thing, is you will take your percent. So let's say that 19.9 and rounded it to 20 here. Divide it by 100, and that gives you the 0.20. So if you take 9 or 20 and you divide it by 100, you're going to get 0.20. So that's where that 0.20 is coming from. And then you multiply it by the mass of your first isotope that you're working with. So the mass of that one is 10. That's boron 10. So that's where that 10 is coming from here. And then percent boron of 11, it's about 80. So they took 80 divided by 100, you get 0.80. And then they took the mass of boron 11, which is 11. And then you multiply this first term out, you multiply the second term out, you add that, and that gives you the 10.8 AMU. So this is your equation. And it's the more general version is right here. The abundance, it has to be in a decimal format. So please remember, you have to have it in a decimal format. If you try to multiply the percentage directly times the mass, that's not going to work. That's going to give you a way big number. Make sure it's in decimal format. Multiply it by the mass. That's one term. Add. Do it again for your second isotope. Add that to the first one. That's your atomic mass. This could keep going. So elements could have more than 2 isotopes. So if you needed a third term, that would be completely fine. Just make sure that it's in the correct format. You have the decimal times the mass of whatever the isotope is, and you keep adding until you're done. So, for example, here, you're trying to get the atomic mass. You have to convert this 40% to a decimal, so 0.40 times 37, and then 0.60 times 35. Multiply each of those separately, and then add them, and then that would give you your atomic mass. So please refer to this example. It's a really good example. It lays it out for you real quick. And here's the general equation if you need that. Okay, so you have all the resources here if you need them. You have my explanation. If you would like more examples shown to you how to actually calculate it, just search this in YouTube. You know, there's so many examples out there, right? Just search average atomic mass, weighted atomic mass. You will get so many examples. So now that I feel comfortable with what I discussed, thank you for watching the video. Please let me know if you have any questions at all. I am here to help.